the Regents Physics course. Topic 1 is math skills. Math is extremely important in physics, so we have a whole topic devoted to math. This is section 1.35, and it's called the math shortcut. And what we'll be talking about in this topic is how to determine the relationship between two variables by looking at an equation that relates the two variables. All right, now we'll be talking about 5 different types of relationships. We'll be talking about direct relationships, inverse squared relationships, exponential relationships, and square root relationships. And what we'll be doing is I'll be explaining to you how you can take an equation that relates two variables and decide exactly what type of relationship exists between those two variables by looking at the equation. There are more than 5 types of relationships in physics and math, but we'll be starting out with the 5 most basic, most common relationships. What I'm going to do right now is just list the 5 of them and show you a graph of each one of the 5. All right, so you have a direct relationship, and the graph of a direct relationship is going to look like that. It's going to be a diagonal line, a straight diagonal line. You have an inverse relationship, right? And the graph of an inverse relationship is going to look like that, right? You have an inverse squared relationship, inverse squared, and you're really not going to be able to tell the difference between an inverse and an inverse squared relationship unless you actually see some of the numbers on the graph. So for now, I'm just going to draw it the same way. All right. You have an exponential relationship. Exponential. All right. And if the relationship were squared, it would go up slowly. If the relationship were cubed, it would go up faster. All right, so that's an exponential relationship. And finally, you have a square root relationship. And I guess I'm going to have to put that over here. Maybe you can write it down here in your notes, but I'm going to put it over here because I'm running out of room down there. A square root relationship. All right, the graph is going to look like this. Okay? So these are the 5 basic types of relationships in physics and math that I'm going to be talking about. Direct looks like that. Inverse looks like that. Inverse squared looks similar to inverse. You can tell the difference if you see the actual numbers. Exponential is going to look like that. Right? It's a curve. It's not straight. It's definitely curved. And a square root is also curved. But you can see it's curved in a different way. All right. So one of the questions that you might be asked in physics is, what kind of relationship exists between two variables? Well, the first thing we want to talk about is, well, what is a relationship? What do we mean by what relationship exists between two variables? Well, if we know what type of relationship exists between two variables, we know how a change in one variable is going to affect the other variable. So in other words, a relationship is like a pattern between two variables. Now, what I'm going to do is talk very, very qualitatively. Actually, a lot of this video is going to be qualitative. We'll be doing some calculations, just to kind of prove our points. But I'm going to be talking now just qualitatively. So again, so that you understand what we mean by the word relationship. Now, let's look at a very simple equation. Perhaps you already know that if you want to calculate the speed, and the symbol for speed is v, it's the same symbol for velocity, they share that symbol. If you want to calculate the speed of an object, you're going to take the distance that object covers and divide it by the time it takes the object to cover that distance. So we have here a nice, simple equation. Now, think about this for a minute. Let me say again that we have to focus on two variables only in the very beginning. We will focus on just two variables at a time. So the first two variables we'll look at here will be distance, right, and speed. All right, now what that means is that we know that the time is the same. The time stays constant. All right, so now think about this. If the distance that some object covers is larger, if the distance is increased or the distance is more in the same amount of time, is that object going faster or slower? Again, if some object covers a greater distance in the same amount of time, is that object going faster or slower than some other object that covered less distance in the same amount of time? What are you going to say about the object that covers more distance in the same amount of time? You say, oh, that object is going faster. Its speed is greater. So common sense tells us that as distance increases, speed increases if time is the same, or time is constant. All right, now another way that you can write this would be if distance increases, then speed increases. All right, and this is a classic direct relationship. You see that distance and speed are directly related. Okay, now let's look at time and speed. All right, so again, if we're going to focus on time and speed, then the distance has to be the same. We're talking about how time affects speed. The distance is going to have to be the same. So let's have a little different scenario here. All right, we have an object that takes more time, takes a longer time to cover the same distance. Much more time to cover the same distance. What are you going to say about the speed of that object that took so long? The speed was lower. It had a slower speed. So common sense again tells you that, we'll put that for direct. Common sense again tells you as time increases, speed decreases. If it takes more time, he's going slower, right? As time increases, speed decreases. And again, that's if distance is the same. All right, now this, all right, the time increases and the speed decreases, all right, the speed decreases, that is your classic inverse relationship. All right, so just getting started. I guess you could copy this down. We're going to do it again more specifically, but this is your classic direct relationship. I want that to write nicely. This is your classic direct relationship. And this is down here is your classic inverse or indirect. They're synonyms. All right, this is your classic inverse or indirect relationship. In a direct relationship, like for example between distance and speed, as one variable increases, the other variable increases also. In your classic inverse relationship or indirect relationship, as one variable increases, the other one decreases. Okay? So now what I'm going to do is talk about each of the 5 types of relationships. We'll look at the graphs, we'll look at equations, and I'm going to show you how to just look at the equation and tell whether a relationship is direct, inverse, inverse squared, exponential, square root. Now, you probably have some idea already that if you have two variables, all right, now you know that this speed here, you see the speed here, v, is really over the number 1, right? Every number that's all by itself is really over 1. So the speed and the distance here are both in the numerator, all right? Numerator on this side, numerator on that side. That's your classic direct relationship. Here, the speed is in the numerator, but the time is in the denominator. Classic inverse relation, right? Directly related, inversely related. We're going to go into that now in more detail so you see very clearly, and it's nice and simple. All right, I need to set this up a little bit and talk a little bit about which variable is the independent variable, which variable is the dependent variable. You might have heard about this in another science class, maybe in biology or earth science perhaps. If we're asking how does a change in mass affect the kinetic energy of an object, like for example, now I don't know if you've ever heard the word mass before, or if you've ever heard the word kinetic energy before. Perhaps you have, perhaps you haven't. All right? Don't worry too much about the words. It's just an example. All right? And we're gonna do this very clearly, where you don't really have to know exactly what all of the words in this video mean. All right? The pattern about how you figure these things out is going to be the same, and it's going to be very simple. But for example, if we have a little boy running, all right, and his mass is 20 kilograms, all right, it's a little 4-year-old, and then he's running at a certain speed. His sister, who's a little older, and she's 40 kilograms, so she has more mass, and she's running at the same speed. So what we're comparing is mass and kinetic energy. We don't care about the speed. The speed of the two children is the same. All right? So we're asking, how does a change in mass, in other words, the little girl has more mass. Her mass is increased. Her mass is greater. How does that affect her kinetic energy compared to her little brother's? All right? So in this case, the mass is the independent variable. The kinetic energy is the dependent variable. In other words, the mass is the variable that we pick first, and we change it to see how that affects the dependent variable. In other words, what happens to this variable depends upon what we do to this variable. Now, we need an equation that relates mass to kinetic energy. All right, so here's the equation. All right, this equation, you can find it. You don't have to memorize it right now. All right, it's on your reference tables. It's on the internet. Kinetic energy is going to be 1/2 the mass times the velocity squared. All right, so there's the equation. Now, what I am saying to you is that when we start talking about this, all right, if you want to know about mass and kinetic energy, and the one that you're going to be changing first is the mass, and you want to know how it affects the kinetic energy, the mass goes on the right side of the equal sign, the kinetic energy goes on the left side of the equal sign. All right, this would be our independent variable, and this would be our dependent variable. Okay, and while we're at it, all right, if you put this on a graph, all right, your independent variable goes here, so here's your mass, and here's your dependent variable, here's your kinetic energy. Okay, there's your independent variable, there's your dependent variable. When you do this math shortcut, put your independent variable on the right side, put your dependent variable on the left side all by itself. You can put all the other stuff on the right side, but the dependent variable needs to be by itself on the left side, all right, to make this easier. All right, now, let me just erase this. And let's look, and let me erase this also. Okay, you know that the mass in this case is the independent variable. The kinetic energy is the dependent variable. Velocity has to be the same. All right, we're only going to talk about two variables at a time for now. All right, now, what about a change? How does a change in kinetic energy, all right, affect velocity? In other words, if I say that some object has more kinetic energy, what am I saying about the velocity of the object? All right, now, if this is your independent variable, the kinetic energy, then we need to get the kinetic energy on the right side, and we need velocity to be all by itself on the left side. So we're going to rearrange this equation to get velocity by itself on the left side, because I want to know how kinetic energy being the independent variable, affects velocity as the dependent variable. All right, so let's manipulate this equation to get velocity all by itself. Let's start by multiplying both sides by 2. All right, so if I multiply this side by 2, all right, and this side by 2, all right, 2 over 1 and 2 over 1. This 2 down here cancels with that 2, and on this side I have 2ke equals, those canceled, mv squared. All right, I divide both sides by m. I want the v by itself. So far now I have 2ke over m. All right, and now I'm going to flip this around because I want the v by itself on the left side. So let me clean up the mess I've made here a little bit. All right, you have, more room on your paper than I have on this board. So you can just keep writing, down. All right, but I'm going to clean things up a little bit here. Okay, and I'm going to flip this around. All right, so I'm going to erase this. All right, keep my original equation here. Back to that. All right, so now, if v squared is equal to 2ke over m, all right, and I want v by itself, I'm going to take the square root of both sides. The square root and the square are going to cancel. Okay, and the equation that shows how kinetic energy affects velocity is going to look like this. It's based upon this equation, all right, but we want it nice and neat mathematically, all right, so v is going to be equal to the square root of 2ke over m. Okay, so again, here we want to know how mass affects kinetic energy. All right, you got your independent variable on the right side, your dependent variable all by itself on the left side. Here we want to know how a change in kinetic energy affects velocity. So we've got the kinetic energy on the right side with whatever else belongs in the equation. Your velocity all by itself on the left side. Okay, so this is a little bit of algebraic manipulation that you have to be able to do in order to move forward in this video. All right, so the first type of relationship that we said we would look at would be a direct relationship. And a definition of a direct relationship would be that when one variable changes, the other changes in the same way. Now do keep in mind that only the way we are having this conversation today, this video, we are only allowing 2 variables to change at a time. All right, we're changing one and seeing how it affects another variable. All the other variables in the equation have to stay constant. All right, they have to stay the same. Now, one way you could say this is that as distance increases, for example, speed also increases. But keep in mind that this also means that as the distance decreases, the speed decreases. All right, whatever one variable does, the other variable does the same thing. All right, now let's look at why the graph looks the way it looks. Okay, so let's draw the graph and see what happens as one increases and the other one also increases. I will use that as the example. So here's the graph, all right? And let's say it's a graph of distance versus velocity. So as the distance is increasing, what's happening to the velocity? All right, so if here we start at 0, 0, then as the distance gets bigger, the velocity also gets bigger. Right, as the distance gets bigger, the velocity gets bigger. Right, as this one goes further to the right, this one goes further up. As this one goes further to the right, as distance gets bigger, velocity gets bigger. Right, as distance gets bigger, velocity gets bigger. As distance gets bigger, velocity is bigger. So what you end up with is a straight line. So what you end up with is a nice straight line. Okay, that should be perfectly straight. All right, so that's what a graph of a direct relationship looks like. Okay, Now, let me show you how you can look at any equation and tell which variables are directly related. All right, I'm going to put a whole bunch of equations up here. All right, some of these maybe you've seen, some of them you haven't seen. All right, but what we're talking about, all right, it doesn't matter whether you know the names of these variables or not. All right, what matters is you're looking at their positions relative to each other and their positions in the equation. All right, so here we go. All right, speed is equal to distance divided by time. All right, kinetic energy is equal to 1/2 times the mass of the object times the object's velocity squared. All right, the gravitational force is equal to the universal gravitational constant times the mass of one object times the mass of the other object divided by r is going to be the distance between those objects squared. Again, don't worry yet. We're just writing some equations up on the board. The gravitational potential energy, right, PEG, the gravitational potential energy of an object is equal to the object's mass times the acceleration due to gravity on that planet, for example, or that celestial body, times the height, all right, of that object. Centripetal force, right, centripetal force is equal to the mass of the object times the velocity squared over the radius, right, of the circle that the object is following. All right. Are there any? Okay, yeah. Let's do the one that we derived earlier. The velocity of an object is equal to 2 times the object's kinetic energy, and then divided by the object's mass. All right. The square root of 2 times the object's kinetic energy and divided by the object's mass. Okay. Now, let's see if any of these objects. Let's see how we can tell which of these pairs of variables are directly related. Okay. First of all, you've got your independent variables on the right side. We're assuming that the dependent variable is on the left side. Okay. Now, keep also in mind that everything is really over 1. Right. This is over 1. All right. Everything that's by itself is over 1. This kinetic energy here is over 1. Right, this mass here is over 1. Right, these have that. Right, this is over 1. Right, this is over 1, etc., etc., etc. All right, so everybody that's by himself is really over 1. Okay, so we can think of this as being in the numerator. All right, this is in the numerator. This is in the numerator. This 2 on the bottom here is in the denominator. All right, this is in the numerator. The distance is in the numerator, the time is in the denominator. Okay, you know this from 3rd grade, right? All these are in the numerator. Okay, this guy is in the numerator. Let me fix him. All right, we don't need to draw the ones, okay? You know that that's in the numerator. These are in the numerator. This guy's in the denominator. All right, this guy here is in the numerator. These guys on top are in the numerator. This guy's in the denominator. Okay, and everybody in here, this is in the numerator, this is in the denominator, but keep in mind everybody here is under a square root sign. Okay, now, how do you tell when 2 variables are directly related? If the 2 variables, now you need to write this down. If the 2 variables that you are comparing, first of all, are on opposite sides of the equal sign, okay? And I'm also going to say that the dependent variable needs to be by itself to make this easy. All right? If your dependent variable is by itself and both of your variables are on opposite sides of the equal sign, then the 2 variables are directly related if they are both in the numerator and neither has a square or a square root, okay, or any exponent for that matter. Neither has any exponent or any square root. And of course, a square root is a fractional exponent, so really you're just saying that there's no exponents on either of them. Okay? So direct relationship, now watch, okay? We're comparing distance and speed. They're both on top, right? They're on opposite sides of the equal sign. They're both in the numerator. This is a direct relationship, okay, between distance and speed. That's not a direct relationship to speed. All right. Opposite sides of the equal sign, okay? They're both on top, all right? Mass and kinetic energy are directly related. The speed has an exponent. He's not directly related to kinetic energy, at least not in a simple way. All right? That's going to be we're going to call that an exponential relationship. All right. Now, here. All right. All three of these, the mass, the acceleration due to gravity, and the height, right, are directly related to the gravitational potential energy of an object. All right, this guy, if the other two are constant, this guy is directly related here. All right, this guy is directly related to PEG, and this guy is directly related to PEG. Okay? Now, G here is a constant. All right, he's not going to change, so we can't even talk about him. Not in this video. All right? But the mass of the first object here, if you increase the mass of the first object, then the weight is going to increase. All right? If you increase the mass of the second object, all right, the weight is going to increase. All right, so these two, this is directly related to the gravitational force. This is directly related to the gravitational force. All right, try these guys. All right, we're not going to talk about this guy right now because he's got a square. He's got an exponent. We're not talking about that right now. But this guy, all right, mass, is directly related to centripetal force. They're on opposite sides of the equal sign, and they're both on top. They're both in the numerator. So there's another direct relationship. Now, the reason we're not going to say that kinetic energy here is directly related to speed is because it's under a square root sign. So that's going to be a different type of relationship. The graph is going to look different. All right? So what I have explained to you here is how to tell. First of all, how to set up an equation so that you can easily tell what type of relationship it is. So far, we've looked at direct relationship. You have to have your independent variable on the right side, your dependent variable on the left side by itself, okay? And then you look and see if they're both in the numerator and neither of them has an exponent, okay, whether it's a square or a cube or a square root, all right, then they are directly related. Opposite sides of the equal sign, both on top, no exponents, they are directly related, okay? So we've talked about how to set up the equation so you can tell easily. We've talked about how to tell when two variables are directly related, and also what the graph of a direct relationship looks like. All right, just before we go on to the inverse relationship, I do want to do an example where we see what exactly happens to the numbers. A quantitative example, what actually happens to the numbers in a direct relationship when you change the independent variable. All right, so for example, let's say we have somebody who covers 10 meters, all right, in 5 seconds. All right, so 10 meters divided by 5 seconds, that person's velocity, all right, is 2 meters per second. Okay, now, what if somebody else covers twice the distance? This person goes 20 meters in the same amount of time, 5 seconds. All right, 20 divided by 5, this person's speed is 4 meters per second. So what I want you to see here, now we said earlier that in a direct relationship, right, and remember, we know that the relationship between distance and speed is direct because, first of all, we're keeping the time we're keeping the time constant, all right? We have the distance and the speed on opposite sides of the equal sign, right? The independent variable is on the right side. The one we want to see what the effect is. The dependent variable is on the left side. They're both in the numerator. This is over 1, so the speed is in the numerator, and the distance is in the numerator, right? They're on opposite sides of the equal sign. They're both in the numerator. Okay, so we have a direct relationship here between distance and speed. Now, what we said earlier in the video is that a direct relationship means when one variable increases, the other variable increases also. But more so than that, look what happened. When the distance was doubled from 10 to 20, the speed doubled also. Remember we said earlier, whatever happens to one variable, the same thing happens to the other variable. So I'm going to say here, if the first variable is, if the distance here were doubled, the speed would double. If the distance were halved, the speed would halve, right? If the distance were 10 times more, the speed would be 10 times more than the original, okay? So it's not just that if one increases, the other increases. If one decreases, the other decreases. The change is exactly the same. All right, so just a little bit more here about a direct relationship. Okay, now we're going to go and look at the inverse relationship.